All right. Physics CP, December 4th, 2020. I have a handout called Conservation of Mechanical Energy. Mechanical energy means all the surfaces are frictionless. All the energy conversions are frictionless. We have an ideal spring here, no friction. We have a ramp here, no friction. We have a surface here, no friction, no air resistance. This is an ideal system. When there is no friction present, we say mechanical energy is conserved, meaning at any moment in time, the total energy is the same everywhere throughout the system. The situation here is we have a ball with an initial mass of, with a mass of 2 kilograms that is initially started from rest at a height of 3 meters above the ground. When you let go of it, it slides. It doesn't actually roll, right? Because it's sliding. It slides down the ramp. At point B, it's 1 meter above the ground. At point C, it's on the ground. At point D, it has come to rest after it has compressed this ideal spring. Labeled here, the spring constant is 50 newtons per meter. The entire worksheet has a table for you to fill in. And the table consists of the 4 different points, A, B, C, D, and 4 different energies, K, UG, US, and E. Oh my goodness. K probably represents what form of energy? Oh man, that student isn't here. Augustine, what do you think the K represents? Oh, best guess. Ah, okay. So it represents kinetic energy. And by the way, do you happen to remember the formula for kinetic energy? One half, right. One half times the mass times velocity squared. Okay, so then there's UG. What kind of energy do you think UG is, Zara? Yes, this is a college style. We're in high school, we would just call it PE for potential energy. Sometimes they call it GPE for gravitational potential energy. And in college, they use capital U, subscript lowercase g. Do you remember the formula for calculating gravitational potential energy? Excellent. M times G times H is correct. Now, I want to talk about us. What is us? Oh, and it says no more students to pick from. Well, let's start through the whole list again. Matthew, let's talk about us. What is us? Yes, and do you happen to remember the formula for calculating spring potential energy? Excellent, that is true. One half times the spring constant, lowercase k, times the distance that the spring is compressed or stretched, squared. This x is the distance it is stretched or compressed. And finally, E. I'll just tell you what E is. E.T. My father's initials. Yes, I am the son of E.T. Haha. E is the total energy, and that is the sum of the kinetic energy and the gravitational potential energy and the spring potential energy. So you could solve this problem using the kinematic equations of motion. However, the way you are to solve this worksheet is to use conservation of mechanical energy. Is total mechanical energy conserved? The answer is yes. Why? Because there is no friction. Briefly, if there were friction, then we would call this conservation of total energy. If there is no friction, we call it conservation of mechanical energy. So I don't really call it total mechanical energy. We either call it mechanical energy if there's no friction, or total energy if there is friction. We have to include the work done by friction. That's a separate handout. All right, so point A, the object is released from rest. From rest. From rest means the velocity is 0. So what is the kinetic energy of this ball at point A? Ray. Yes, excellent. 0 joules. Not to be confused with OJ, neither OJ Simpson nor orange juice. It is 0 joules. Sometimes they put a slash through it, meaning that's the number 0. UG. We need to calculate UG. The mass of the ball is 2 kilograms. The height is 3 meters. We assume it takes place on Earth. Calculate, please. What do you get as being the gravitational potential energy of a 2 kilogram ball on Earth? Whoops, I typed the wrong thing. At a height of 3 meters above the surface. Jaden. I agree. 58.8 joules. Let's talk about us. If the ball is at point A, how much is the spring way over on the other side of the diagram being compressed by this ball at point A? Nathan, what do you say? How much energy is being stored in the spring when the ball is at point A? Nathan. You don't. You have no idea. You can't figure this one out. The ball's over here at point A. The spring is way over there at point D. The ball is not at D. The ball is at A. So how much is this ball squeezing that spring when the ball is over here? Yes. There. So much for us. 0 joules. Because the spring is not being compressed. This ball here is a snapshot later in time. We are still at the beginning of this problem. The ball is really here right now. All right. And finally, what is the total energy in this problem, Tony? No units. Joules? Oh my goodness. 58.8 joules. All right, children? Now, put your thinking caps on. Mechanical energy is conserved because there is no friction. The total energy at point A is 58.8 joules. So, what is the total energy at point B? Joseph Q. Excellent. Absolutely correct. And someone else? What is the total energy at point C? Fabian. Absolutely correct. And finally, once this ball has compressed the spring at point D, what will be the total energy, Siddharth? Yes. So do not solve for the remaining spaces using kinematic equations of motion. Among other things, the accelerations aren't constant here. Instead, use the principle of conservation of energy and treat this as x plus y plus z equals 58.8 UC. X plus y plus z equals 58.8. And at any point in the problem, we can give you two of these. So you solve for the one unknown. Let's try it at point B. At point B, they are not telling us how fast it's moving, but they are telling us that it is 1 meter above the ground. So which of the three variables should we calculate? K, UG, or us? Eric, at point B. Should we calculate K, UG, or us? Eric. I agree. Let's get on with it. Students, calculate the gravitational potential energy of this 2-kilogram ball that is located 1 meter above ground level. Harshith, what do you get? A 2-kilogram ball on Earth 1 meter above the ground. 33. No units. All right. Zara, do you agree? Uh-oh. Would Yeah, so did I. 19.6 joules. 2 kilograms times 9.8 meters per second squared times 1 meter height is 19.6 joules. All right, next question. Here at point B, how much energy is being stored in this compressed spring? When the ball is at point B, how much energy is being stored in the compressed spring, Josh? Really? So even though the ball is way over here and the spring is way over there, oh man. 0 joules. All right, children. At this point, you should realize that we have the value for UG, the value for us, the value for the total, and by subtraction, you should be able to figure out the value of the kinetic energy at point B. Dylan, what do you get? Aw, child. What is the kinetic energy of the ball when it is at point B? I don't know. What are the units? Joules. Always put the Okay, well, let's see. Jacob, do you agree? All right, children. Your homework assignment will be to not only complete this table, but then go on and answer the 3 questions, and then go on and do the rest of the handout. Look at this fun bottom one. So the ball in number 2 is going to begin from rest up here. There is no friction anywhere on this handout. Slides down, goes through B. It does the loop at C and D. Then at the end, it makes its way up a hill to compress a spring. And the table is like the one above it. So point A, B, C, D, and E are different snapshots of the same 3 kilogram ball. And we'll pretend that this has 3 sig figs for your calculations. So 3 sig figs, 3 sig figs to figure out stuff. So call this 3.00 meters, 1.50 meters, 50.0 newtons per meter. And there's your homework.